This video is about classifying differential equations. Just as a brief recap, a differential equation is just an equation that contains the derivative of an unknown function. And our goal is to find that unknown function. So here's one example that we looked at in the last video. And it turned out that y equals e to the 3x or a constant times e to the 3x would work. It would satisfy this differential equation. Here's another example. That is another differential equation. That we'll learn how to solve in this class. So both of these are differential equations. Here's another one. That's a differential equation as well. But the method that we use to solve this equation is slightly different from the method, or it's actually very different from the method that we use to solve this equation. And that's very different from the method that we use to solve this equation. And we're going to use lots of different methods to solve all of these different differential equations. It's actually very similar to the idea of solving different equations with different methods in algebra class. In algebra, you started with something that looked like this. Maybe you have like that 2x plus 6 equals 0. You're going to solve that equation using one method. And if you have this equation, you might solve that equation using a different method by factoring. This is one that you may want to solve by completing this square. This is one that you would probably solve by squaring both sides to get rid of the radical. But in algebra class, you basically learned techniques for solving different types of equations. And in each case, you were trying to find x. Now, these equations might mean something. We're going to talk about what these differential equations mean in a little bit. But for right now, we're just going to stay in the abstract and say, this equation requires a different method of solution than this one, as does this one, as does this one. These are very similar. Turns out there are lots of solution methods to differential equations. We're going to learn about, I'd say probably 12 or 13 of those methods in this course. But in order to decide what method is appropriate to solve a differential equation, we have to classify that differential equation first. So we're going to classify differential equations by type, by order, by linearity, and homogeneity, and also by the nature of the coefficients. These 5 characteristics are going to help us decide which method is appropriate for solving a particular differential equation. So let's talk about this first way of classifying differential equations. We classify differential equations by type. Either we have ordinary differential equations, or partial differential equations. And I will abbreviate those as ODE or PDE. This class is primarily about solving ordinary differential equations. Ordinary differential equations are differential equations that contain ordinary derivatives only. So those are just derivatives where the original function was a function of one variable. A partial differential equation is a differential equation that contains partial derivatives of our unknown function. Okay, so this is an ordinary differential equation, and this is an ordinary differential equation. This is a partial differential equation. In order to recognize ordinary differential equations versus partial differential equations, we need to remember some basic notation for derivatives. So let's review that. So we've got prime notation. Prime notation is used for ordinary derivatives only. And so we might have y prime, that's the first derivative, y double prime, that's the second derivative, y triple prime is the third derivative. Now after that, we don't write y quadruple prime, we start writing the order of the derivative, that's the number of derivatives we're taking in parentheses. So this is this is the fourth derivative of y with respect to some variable. It's not y to the fourth power. If those parentheses weren't there, I would assume that this is y to the fourth. But since the parentheses are there, that tells me I'm talking about the fourth derivative of y with respect to some variable. Now, one of the downsides of prime notation is the independent variable isn't listed here. The nth derivative can be written that way. And that's the nth derivative of y with respect to some variable. So that's prime notation, and it's used for ordinary derivatives. We never use this for partial derivatives. Now, another notation, and this is probably one of my favorite notations, is Leibniz notation. This can be used for ordinary derivatives, and partial derivatives. So this y prime might represent the derivative of y with respect to x. In Leibniz notation, instead of writing y prime, we write dy over dx, and normally that's just pronounced dy dx. Now the second derivative of y with respect to x looks like this. It looks like that second power is on the d, and the second power is on the x. It's just notation. That's the second derivative of y with respect to x. Now, one way that you can remember this is it comes from this operator notation. I'm taking the derivative with respect to x of the derivative of y with respect to x. And it's almost as if I were to multiply those two together, I get something that looks like that. It's not exactly the same thing because this isn't really like dx times dx quantity squared in the denominator, but it helps remind me that we're going to see it like this. You have two d's up here, and then you have the dx and the dx down there. So that's a second derivative in Leibniz notation. Third derivative looks like this. So it's the derivative of the derivative with respect to x of the derivative of y with respect to x. And again, you see the d, the d, the d, that gives you the d cubed. And then you see dx, 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 that's dx quantity cubed. So that's the third derivative of y with respect to x. So this is my Leibniz notation right here, and right here, and right here. And these are all ordinary derivatives because of these d's. I'll show you partial derivatives in a minute. The nth derivative of y with respect to x looks like that. Okay. So that could be used for ordinary derivatives, like I've shown you right there. Leibniz notation can also be used for partial derivatives. So maybe you're talking about the partial of y with respect to x. So that's taking the derivative of y with respect to x, treating the other variables as constants. Often u is our dependent variable. It tends to be used as our dependent variable. So we'll see the partial of u with respect to x, or the partial of u with respect to y, or the partial of u with respect to t. All of those are first partial derivatives, and I see that little partial sign. That indicates to me that even if I don't know what the other variables are, that y depends on more than one variable. X is one of them, And we're taking the derivative of y with respect to x, and we're treating all the other variables as constant. Same thing here. U depends on more than one variable. T is one of them. I'm taking the derivative of u with respect to t, and I'm treating all the other variables as constants. Or we could take the partial with respect to u with respect to t twice. We can also do mixed partials. Maybe you want to take the partial of u with respect to x first and then y. Now this is a little bit counterintuitive. This mixed partial says, it's not read from left to right, it's sort of read from right to left. You're taking the partial of u with respect to x and then taking its derivative, partial derivative with respect to y. And so even though you have the y here and then the x, you actually differentiate with respect to x first and then y. But I think once you write it in this other form with the operators, it makes a little bit more sense. So let's say the nth derivative of u with respect to, let's say t looks like that, and so on. Okay, so that's Leibniz notation. Now we also have dot notation. And this is used for ordinary derivatives only. And here, every dot indicates differentiation with respect to t. And t is usually representing time. Okay, so x dot is the derivative of x with respect to t. X double dot is the second derivative of x with respect to t. It's a very convenient notation. It's really easy to write. It's really fast to write. And we know, because of the fact that we're using dots, we know that the independent variable is t. But again, this is used for ordinary derivatives only. Now, I've been using these terms dependent variable and independent variable. I guess I should review what that is just briefly. If we have y as a function of x, the dependent variable is y. And the independent variable is x. As we're letting x vary, we're thinking of it as being independent. And then no matter what x is, this equation is going to tell us what y is. So we're thinking of y as depending on x. Similarly here, if u is a function of x and t, the independent variables, I'll abbreviate that IVs, are x and t. And the dependent variable here is u, because u depends on x and t. Now here, it's a little different because x is often our independent variable. We often think of y as a function of x. That's not what we see here. When I see that x dot or that x double dot, I'm saying x is a function of t, and I want you to take its derivative. Or I want you to take its derivative twice. Let me get that. So we've got our prime notation, we've got our Leibniz notation, we've got our dot notation. The last notation that we need is subscript notation. This is used for partial derivatives only. So u sub xx, u sub xt, u sub yy, u sub yx, u sub t. Those all indicate partial derivatives. I guess I should start with u sub x, u sub y, and u sub t of u with respect to x, y, and t. I'm just using x, y, and t because u usually depends on x or y or t when you study partial differential equations. Now this is the first partial of x with respect to u. Take the derivative with respect to, I said it backwards. This is the first partial of u with respect to x. We're taking the derivative with respect to x and we're treating all the other variables as constants. Now this is the second partial of u with respect to x. So in Leibniz notation, we just write it this way. We take the partial derivative with respect to x twice. Now here is one way where subscript notation and Leibniz notation differ. When I see this, the order that I'm applying that derivative is from left to right. This actually tells me I should take the partial of u with respect to x first, and then take its derivative with respect to t. In Leibniz notation, that looks like this. So that is equal to that. So notice that that says tx and that says xt. This you read from left to right. You take that derivative first, then that derivative. This Leibniz notation, you read from right to left. You do this derivative first and then this one. But the reason we do that one on the right first is because we're thinking of it as an operator. We did the one closest to that function first, and then we go outside and outside and outside, and we sort of work our way out. Okay, so if you see subscripts, you know you're looking at a partial differential equation. If you see dots, you know you're looking at an ordinary differential equation, provided that there are no subscripts or partial derivative signs. Normally we don't mix notation in one differential equation, you usually just use one of these. With Leibniz notation, if you see D's, those are ordinary derivatives. If you see these little partial signs, you know those are partial derivatives. And primes indicate ordinary derivatives. So we often need to classify a differential equation by type. It's either an ordinary differential equation or a partial differential equation. That's an ordinary differential equation. That one's an ordinary differential equation. The reason is that involves primes, and that's a partial differential equation. Okay. We also classify differential equations by order. The order of a differential equation is the highest order derivative appearing in the differential equation. If you've had to take the derivative twice, even if it's a partial derivative, it counts as a second order derivative. So let's say we've got this. That's the second partial of u with respect to t equals the partial of u with respect to x. So that's a second order derivative, that's a first order derivative. So this is a second order partial differential equation. Now this one is can be a little tricky, but if you remember that those parentheses indicate the order of the derivative, it will help you. That's not y to the fifth power, and that's not y to the fourth power. That's the fourth derivative of y, and that's the fifth derivative of y. That's the second derivative, and if there's no derivatives there, that's just y. We can call that the zeroth derivative if we want to. The highest order derivative is the fifth derivative. So this is a fifth order differential equation. Since we have prime notation and those parentheses, that's also prime notation, we know that this is an ordinary differential equation. Okay, this one. Well, first I notice that there's only one derivative in it. That 2 there and that 2 there indicate that that's the second derivative of x with respect to t. This is a second order derivative, or second order differential equation. And since those are d's and not partial signs, this is an ordinary differential equation. So I've got a second order PDE, a fifth order ODE, a second order ODE. Okay. And this is a PDE. Notice we've got partial derivatives. Now careful here. That's a second partial of u with respect to x, so that's a second order derivative. This is actually a third order derivative. This says take the partial with respect to y twice first, and then take the partial of that result with respect to x. So this is a third order partial differential equation. Okay, now first order differential equation might look like this. Maybe you've got sine of t times dy dt plus, let's say, cotangent of t times y equals 2. Well, there's a first derivative right there. And since that's a d, dy over dt, it's a first order ordinary differential equation. Okay. All right, we classify differential equations by type. They're either ODEs or PDEs. We classify them by order. I want to know, are they first order, second order, third order, fourth order, nth order? Next, we're going to classify differential equations by linearity. Now, I'm going to focus on an ordinary differential equation at first, but the principles are going to hold for partial differential equations as well. So let's say an nth order ordinary differential equation, is called linear if the following, or if it can be written in the following way. You take the nth derivative of y with respect to your independent variable, which I'm going to call x, and you multiply it by some coefficient function. And then you add another coefficient function times the next lowest derivative of y with respect to x. And then you add another coefficient function times the next lowest derivative of y with respect to x, and so on. The last one is a sub 0 of x times y. It's a zeroth derivative times that other function equals g of x. Now I know that looks like alphabet soup, but all of these functions out front would be given to you. So this is given, and 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 this is given. Now, sometimes the differential equation doesn't immediately look like this. Sometimes you've got to rearrange it to make it look like this. But what makes it linear is that those coefficient functions and the function on the right-hand side depend only on your independent variable. So I'll say the coefficients a sub n minus 1, a sub n minus 2, all the way down to a sub 0, and the function on the right-hand side, g of x, or g, all depend on well, let's say all depend at most on x. If they depend on y, if they depend on y's derivatives, they're out. It's not an ordinary, or it's not a linear differential equation anymore. Also, y and y's derivatives appear in the differential equation raised to the first power or not at all. So let's say the 0th power. So they don't appear in the equation at all. So this is raised to the first, this is raised to the first, this is raised to the first. All of those derivatives and y itself, they're all raised to the first. If that's true, then you've got a linear differential equation. Now, this third quality of a linear differential equation is actually already accounted for in these two conditions, condition 1 and condition 2. But it's helpful, I think, for students to think of it this way. We can't have any composite functions involving y or y's derivatives. So you don't have y inside an exponent. You don't have y under a square root. Okay. Another thing is you generally can't have a product of several derivatives of y or functions of y and derivatives of y, but that's really accounted for by this coefficient condition. I can't have a y double prime times a y triple prime, because if I did, then the coefficient of one of them would be the other one, and that wouldn't be a function of x only. Okay, so that's what it means to be linear. Let me show you one more thing about linearity. I think this helps some people to understand a pattern. The equation of a line in 2D, of course a line's in 2D. Equation of a line can be given by a constant times x plus a constant times y equals a constant. So that's linear. It's linear in x and y. A, b, and c are just constants. In Calculus 3, when we came up with tangent planes, we sometimes call those the linearization of some function. So you might have a linearization of some function, or you might just have the equation of a plane. That's ax plus by plus cz equals d. Notice that the variables that you're interested in both of these cases are all raised to the first. And they've just got constants out front and then just some other constant on the other side. That's what we have here. I know it looks much worse, looks much, much worse, because you've got variables up front. But I don't want you to think of it that way. I want you to think of this as not depending on y, and not depending on y, and not depending on y. If those coefficients don't depend on y or y's derivatives, and the right-hand side does not depend on y or y's derivatives, and all of the derivatives of y and y itself are all raised to the first power, then the differential equation is linear. Okay, kind of like this. So those coefficient functions are playing the role of these coefficients here. These coefficients are always constants. The other coefficients, they don't have to be constant, but they can't depend on y or y's derivatives. So let me show you some examples. Let's say you've got dy dx plus 2x times y equals sine of x. Let's go through all of the classification. First of all, I noticed that I've only got one derivative here. It's a first derivative, so this is a first order differential equation. and it's an ordinary derivative. So this is a first order ODE. Now the question becomes, is it linear? Is it a linear or nonlinear ODE? If it's linear, if it satisfies that equation on the last page. So if the differential equation can be written like this, it's linear. If not, we call it nonlinear. Let's see. Let's look at the coefficient functions. There's an implied 1 there. The coefficients are 1, 2x, and sine of x. The question is, do those depend only on the independent variable? The independent variable is x, so yes, those depend only on the independent variable. I've got y, the derivative of y with respect to x there and y there. Both of those are raised to the first power. So this is a first order linear ordinary differential equation. We're going to learn to solve these pretty quickly, pretty soon. Let's look at another one. So you've got e to the 2x times the third derivative of y with respect to x plus natural log of x times dy dx minus y equals 3. Well, let's figure out whether it's an ODE or a PDE. Those are D's, those D operators, those are ordinary derivatives, so this is an ODE. Then I want to classify it by order. It's a first derivative, that's a third derivative, so this is third order. And now the question is it linear or is it nonlinear? To figure out if it's linear or nonlinear, I look at the coefficient functions. And I ask myself, do those depend on x only? At most on x. It's okay if they're constants. It's like y of x equals 3. Totally fine. Just a constant function. That depends on x. That depends on x. That's just a 1. Doesn't even depend on x. And that doesn't even depend on x. So those are good. The coefficients are fine. Well, let's look at the derivatives and y itself. Is it raised to the first? Yep, it's a third derivative raised to the first. That's a first derivative raised to the first and y raised to the first. So this is linear. Okay, I'm just going to change it up just a little bit. Okay. Still an ODE because those are still ordinary derivatives. But be careful here when you're looking for the order. Don't be distracted by that exponent. That is telling you to cube something. This inside is the second derivative of y with respect to x. So this is saying, take e to the 2x, multiply it by the second derivative of y with respect to x, cube that. Since I've got that second derivative cubed, it's not raised to the first power, but it's raised to some other power, this is nonlinear. And the highest order derivative in the differential equation is the second order derivative. Now, I can't write it out exactly the same way. Over here, when I wrote down my coefficient functions, I said the nth coefficient, the coefficient of the nth derivative was a sub n, and the coefficient of the n minus 1th derivative was a sub n minus 1, and the coefficient of the n minus 2 derivative, well, that's a sub n minus 2, and so on. So the second derivative had a coefficient of a sub 2, first derivative had a coefficient of a sub 1. I can't do the same thing when I have a partial differential equation because the order of the derivative and the number of coefficient functions, they just don't line up. So, but the qualities are the same. A partial differential equation will be linear if the coefficient functions depend at most on the independent variables. So our independent variables are usually x and y, or maybe x and t. And then the dependent variable and the dependent variable's derivatives can only appear to the first power or the 0th power. So they just appear by themselves, multiplied by some coefficient function, or they don't appear at all. You can't have that dependent variable raised to the 1/2 power. We can think of that as a composite function involving y or y's derivatives. If that happens, it's fine. It's just nonlinear, and nonlinear differential equations are a little bit harder to solve. So let's keep all of that in mind and look at a PDE. Okay, so first of all, I notice that it's a PDE because I've got subscript notation. And I look at my first derivative. This is the first derivative of u with respect to t, treating the other variables as constants. And this is the second partial derivative of u with respect to x. So I've only got those two derivatives. The highest order derivative is the second derivative. So it's a second order PDE. And I look at the coefficient functions. If I'm trying to determine if a differential equation is nonlinear, I want to write it like this. I want to get all of the terms involving my dependent variable on the left-hand side and all the other terms on the right-hand side. In this case, it's already in that form. Then I look at my coefficient functions. Those can depend at most on the independent variables. Now, we weren't told which variables were dependent and which variables were independent, but we can tell from context what's going on. We can tell from context that u depends on x and u depends on t. So u is a function of two variables, and they are x and t. So my independent variables here are x and t. Those are free to vary. And my dependent variable is just a single variable, and it's u. Okay, so we've got that. All right, so if I'm trying to determine if a differential equation is linear or nonlinear, first I move all the terms involving u, my dependent variable, to one side, and they're already on one side. And then I look at the coefficient functions. This coefficient function and this coefficient function, the question is, do they depend on x and t only? Yeah, that depends on x and t, and that depends on x and t, so we're good there. Then I need to look at u and u's derivatives. Are they raised to the first power? Sure. Okay, so this is a second order linear partial differential equation. Now this one, let's make it xxx. This is a third order differential equation because I'm taking the third partial derivative of u, or the third partial of u with respect to x. And it's a partial differential equation. And the question is it linear or nonlinear? Well, when I'm trying to determine that, I put all of the terms involving u on one side, and they're already on one side. And then I look at the coefficient functions. Well, I can think of this one as a coefficient for this one, or this one as a coefficient for this one. Either way, they're multiplying each other, so that makes it nonlinear. Okay. Now let's say this is your differential equation. Now, first I notice I've got prime notations. This is an ODE. And the highest order derivative is a third order derivative. So it's a third order differential equation. Now, generally, if we want to determine whether a differential equation is linear or not, we need to write it in this form. So we're looking for this. We need all the y's on one side. Every single term involves y or y's derivatives. It's got a derivative times a coefficient function, and then a zeroth derivative times a coefficient function. And then I've got the function of my independent variable by itself on the other side. So when I see this, I see that 3y on the right-hand side, I think to myself, I want to get that over here. So we'll subtract the 3y from both sides. To get there. Okay. And now we look at y and y's derivatives. Are they all raised to the first? They are. Look at the coefficient functions, 1, -2, -6, -3. And the function on the right-hand side, did they depend on the independent variable only at most? That t? Yes. So this is linear. But if I change it just a little bit, that square root makes it nonlinear, because now y is not raised to the first power, it's raised to the 1/2 power. So this is still a third order ODE, but it's nonlinear because that y is raised to the 1/2 power. Okay. So those were our first 3 ways of classifying differential equations. By type, they're either ordinary differential equations or partial differential equations. Order, want to know is it first order, second order, third order, so on. And then we looked at linearity as the differential equation, linear or nonlinear. Now, another really important quality of differential equations is whether or not they're homogeneous. It definitely determines which methods we will use to start solving the differential equation. We're going to use homogeneous in 2 different ways in this class. I'm sorry that we're going to use the same term in 2 different ways. I'm going to show you the first way now, and then also by nature of the coefficients. Actually, let's do nature of the coefficients first and then talk about homogeneity, and then we'll look at examples of both. So I'm doing this in slightly different order. Do 5 first, nature of the coefficients. A differential equation generally has constant coefficients or variable coefficients. Okay, so actually, let's just look at this example right here. The coefficient functions are the coefficients of y's and y's derivatives. Or the coefficients of your dependent variable, which is usually y, and its derivatives. So in this example, the coefficients are 1, -2, -6, and -3. If those are constant, there's a very simple, beautiful method to solving the differential equation. So this is once I've rearranged it so that I've got all the y's on one side, when I identify the coefficients of y and y's derivatives, I see they're all constants. So that is a constant coefficient differential equation. If the coefficients are non-constant, like here, 1, 2x, or here, e to the 2x and natural log of x, or here, sine of xt plus t cubed and t squared minus 3, those are called variable coefficient differential equations. Okay, now let's talk about homogeneity. If the coefficient functions are constants, it's a constant coefficient equation. If the coefficient functions have variables in them, the independent variables generally, then it is a variable coefficient differential equation. So a differential equation is either homogeneous or non-homogeneous. And let's look at that standard form for linear differential equations. So let's say that this is our standard form. I'm calling it standard form. I'm not sure if that's actually the right term. So I've got my differential equation written in this form. If I've moved all my y's to one side, and then I look at the function on the right-hand side, if the function on the right-hand side is 0, the differential equation is called homogeneous. If not, it's not homogeneous. So let's write that down. We'll say move all terms involving the dependent variable and its derivatives to one side, and all other terms to the other side. So you've got the dependent variable terms over here, and then g of x. And this is the sum of the terms that do not contain the dependent variable. If g is equal to 0 all the time, then the dE is homogeneous. We call it homogeneous. If there's any x value where g is not equal to 0, then the dE is called non-homogeneous. So actually, I don't think well, actually I have a couple homogeneous equations. Let's look at these again. So you move all the y terms to one side and all of the terms that do not involve y to the other side. And actually, this is already written in that form. So we say it's a first order linear ordinary differential equation. The coefficients are 1 and 2x. So it has variable coefficients. Because that coefficient depends on x. First order linear ordinary differential equation with variable coefficients. And the question was, is this equation homogeneous or not? Well, when the y's are all over here and the functions of x only are over here, well, that's not 0, it's sine of x. So this is non-homogeneous. This is a first order linear, well, actually, maybe I'll put non-homogeneous first. This is a non-homogeneous first order linear ordinary differential equation with variable coefficients. All of those qualities will affect the solution method that we use to approach solving this problem. This is a third order linear ODE. It has variable coefficients. And it's non-homogeneous because we've got a 3 over here. So this is a non-homogeneous third order linear ODE. This is the second order nonlinear ODE. We've got this 3 over here, so it makes it non-homogeneous. And we've got variable coefficients. So the coefficients are e to the 2x and natural log of x and a 1. So non-homogeneous because of the 3. And they have variable coefficients because of the e to the 2x and the natural log of x. Okay, got variable coefficients because that depends on x and t and that depends on x and t. So this is a second order linear PDE with variable coefficients. And it's homogeneous because the right-hand side is 0. Okay, so this is a third order nonlinear PDE. And this does not depend on U at all. So it's on this side by itself. So that is our G of X and T. So this is non-homogeneous. And there's only one coefficient, and that's a 1. So I would call this constant coefficient. It's a little bit ambiguous, isn't it? Because you're thinking that could be thought of as a coefficient of that one and vice versa. But whenever we've got a product like this involving the dependent variable, we just look at the coefficient of the product. So we're going to call that constant coefficient. This one has constant coefficients, and because the right-hand side is e to the t, we had to rearrange it to get all the y's on this side. But the coefficients are 1, -2, -6, and -3, so it's constant coefficient. So this is a homogeneous, or non-homogeneous, excuse me. Third order linear ODE with constant coefficients. Okay, and this is non-linear, or this is non-homogeneous because of the e, the t, and it has constant coefficients as well. It's the same ones as those. Okay, so that is how we classify differential equations. You've got some problems in your homework where you're asked to classify. It'll be a very simple question. I'll just give you a differential equation and I'll ask you to classify the differential equation by these 5 characteristics. And later in the course, this is going to be really important because if the differential equation is linear, it's nice and easy to solve. We're only going to solve ODEs in this class. The order depends or determines which methods are appropriate. Homogeneity determines which methods are appropriate, and the nature of the coefficients also determines which methods are appropriate. So make sure you're comfortable with all of this terminology and with classifying differential equations by these characteristics.